So building on the concept of the moment of inertia, we now come to the topic of torque. And the rotational effect that's caused by a force is known as torque. And so in general, the way that you apply this, or the way that you think about it, is you apply a torque when you're opening a bottle of pop, whenever you tighten a screw with a screwdriver, whenever you turn on a tap, you're applying a torque. There's two main influences on torque: the applied force, so if you turn harder, you're going to produce more torque, and radius. So if you apply that force at a greater radius, you will apply more torque. So here, let's consider the following diagram of a rod with a pivot at one end. And this could be, you could think about this as basically the top-down view of maybe a cupboard. And there's a reason why the handles of doors are as far away from the hinges as they can possibly be, and it's because we want to maximize the radius, the distance from where we apply a force to the pivot point. And so here in this case, if we wanted to apply some force at a distance r from the pivot, we would produce a torque. The force, of course, doesn't have to be perpendicular to the radius. It can be directed at several different angles. And we measure the applied force, the angle at which it acts. We always measure it with respect to the radius. Okay, so it's always measured with respect to the radius. It's not measured with respect to the perpendicular. And so we make a note that in order to rotate this rod, there's only one component of that applied force that really matters. And that's the perpendicular force. And of course you know this, because if you tried to open a door by pulling on the doorknob in the direction of the pivot, it wouldn't swing open. You have to pull at right angles to the pivot in order to, at right angles to the radius of the door to be able to get it to open. So really, it's only the perpendicular component of force that's important. And so because the applied force can be directed at different angles, we call that theta. And using right angles, we can resolve the applied force. So here's our applied force, and it acts at some angle theta with respect to the door. So the vertical component of this is F sine theta. And we find a formula for torque. Torque is equal to R times F sine theta. The expression implies that we know the direction of rotation. And so more formally, torque is a vector, which is perpendicular to the plane created by R and F. So we have a little diagram here. The plane R and F would be perhaps the flat surface of your desk. And the torque vector is perpendicular to both R and F. And you may have seen something like this before. The magnetic force acts perpendicular to the magnetic field and to the current. And there's other examples in physics. But basically, this is described by the cross product. And mathematically, torque is the cross product of the radius and the force. And we would use the right-hand rule to determine the direction of torque. But we're not going to get into that amount of detail at this point. To open a door, you provide a 45 Newton force at an angle of 5 degrees from the perpendicular, a distance of 0.6 meters from the hinges. What torque is acting on the door? So we'll draw a little diagram. We'll say we're going to push this door. And we push it at an angle of 5 degrees to the perpendicular. So of course, because the angle theta is defined as between the radius and the force, we need to do a little subtraction first. Theta is equal to 85 degrees. And the distance away from the hinge that you are pushing is 0.6 meters. So we can now say that torque is equal to Rf sine theta. Make a substitution for our numbers. 26.9 Newton meters is the torque that's applied to that door. Newton's second law can be rewritten now. We start off with F equals ma, but we know that torque is equal to R times F when they're acting perpendicular, and A is equal to R times alpha. And so having these definitions, we can make a few substitutions. Torque over the radius is equal to F, and A is equal to R alpha. So we can simplify and rearrange. Torque is equal to mr squared alpha. But mr squared, if you'll remember, was the general definition of the moment of inertia. And so we can rewrite Newton's second law as torque equals I alpha. So the net torque that is acting is equal to the moment of inertia times the angular acceleration that is applied. And there it is in print. Just as force causes an acceleration, torque causes an angular acceleration. So here's an example. With a force of 30 newtons, a rider pushes down on the rim of her bicycle wheel. We'll assume with her hand. And that's got a diameter of 0.600 meters. Let's find the applied torque and the mass of the wheel if the wheel experiences an angular acceleration of 26.5 radians per second squared. So here's a little diagram of the bicycle wheel. The force is acting perpendicular to the radius, and the radius would be 0.6 divided by 2, so 0.3. Those are our knowns and our unknowns. And so now we'll say, okay, well, let's find first the torque. Torque is equal to R times F. Sine theta term is irrelevant here because theta is 90 degrees and the sine of 90 is 1. 0.3 times 30 is 9. So the torque acting on this bicycle wheel from the rider is 9 Newton meters. We can now use this result and say, okay, well, the torque is equal to I alpha. We know alpha, we've just found torque. So we can make a quick substitution, and we can find that the moment of inertia of this bicycle wheel is 0.3396. And if you look back into your notes, you will discover, oh, well, a bicycle wheel is actually just like a rotating ring of mass m, or a hoop of mass m, when it's rotating about its center. So a formula for the moment of inertia is I equals mr squared, because this bicycle wheel fits the general definition for this moment of inertia. And so if we substitute in here, we can find that the mass of the bicycle wheel is about 3.77 kilograms. And that's a quick look at rotational dynamics.